Welcome Calc students to our video notes lesson on section 3.7 part 2, where we're going to take a look at differentials and how to use them to approximate error. So what is a differential? A differential is basically a measurement where we find a small change in x and then a related change in y. So I say small change in x because I'm calling it dx. So if you remember, dx comes from delta x, which is referring to a change in x, like an actual physical change between two different x values. dy comes from the notation delta y, which means the same thing, a physical change between two y values. So these differentials are kind of looking at how a small change in x affects the change in y. So for dy, we're going to use this formula right here. The differential of y is equal to the derivative of f times the differential of x. And this is for a very small change in x. A change in x that's almost zero. So it's non-zero, but it's very, very close to zero, which is why we're going to go ahead and call it dx. We're going to think of it as delta x is approaching zero and is therefore equal to dx, so to speak. Okay, so where does this come from? This stems from the idea of the derivative, which is a rate of change. And it's basically taking a slope of a line connecting 2 points. So this delta y is like a change between two y values. The delta x is a change between two x values. And what we did in chapter 2 is we looked at what would happen to that slope if I let the change in x go to 0. So you may remember this limit formula from chapter 2, where I was taking two different x values, x and x plus delta x, and getting two different matching y values. I subtracted those y values and I subtracted those x values to get this quotient, where in the denominator I just had delta x. And then I let that delta x go to 0. That was basically this quotient, but letting the delta x go to 0. When you let delta x go to 0, that gives rise to the actual derivative, the instantaneous rate of change, the slope of a line not at 2 points on the function, but only at 1, the slope of the tangent line. So we're using that concept here, but we're saying, okay, delta x is going to 0, it's close to 0, but it hasn't actually gotten there yet. That's where differentials come in. So differentials are kind of used to approximate different changes in x and y, using this idea of the derivative, but not letting delta x get all the way to 0. So dx is some very, very small value. It's a very, very small change in x. So because it's not exactly 0, in this context of differentials, we can multiply it to the other side. We can multiply it to both sides, and that gives me this formula, which is the one you see over here. So this dy is an approximation for the change in two y values on the graph of y equals f of x. And this dx is a number that is very close to 0. It is a very small change in x. This is the instantaneous rate of change of y with respect to x, slope of the tangent line. And then this is the related change in y, or the approximate value for the related change in y between two y values on the graph of f of x. So just a quick little summary of the slight difference between dy and delta y. Let's just take a look down here. So remember, when you start out with a change between two y values divided by a change between two x values, you're just looking at rise over run, change in y over change in x. But as you let that change in x go to 0, that's turning into the derivative, dy over dx, an instantaneous change in y over x at 1 point versus 2 points. So it's kind of like as delta x goes to 0, then delta y is becoming more and more closer to dy. So when you're at a point where delta x is very close to 0, then you can use that dy as a decent approximation for the change in y, the delta y. Let me kind of show you how that works in this picture over here. So when we talk about delta y, the triangle one, the change in y, we're saying if you were to take two distinct points on the graph of f. So let's say this curve is the graph of f. I have one x value at c, but then I add a little bit to it. I add a little change in x, and I get a new x value of c plus delta x. Plug that in. That'll give me two different y values, f of c plus delta x and f of c. So delta y is what you get when you subtract those two. It's like the actual physical difference between those two y values. So it's this length right here is my delta y. You can see it right there. Okay, so then what's dy? Well, dy would be the change in those values on the tangent line, because dy is equal to the derivative of f at c, right? Because I'm using the tangent line, the line tangent to the curve at 1 point instead of crossing it at 2 points. So I'm using f prime c there. So this equation is basically like a point slope form. This is a change in y. You can think of it as y minus y1. Here's my slope, right? My slope of that tangent line. And then dx is like my x minus x1, right? Change in x. So this is the equation for this tangent line. dy would be the change in the two y values from c to c plus delta x on the tangent line. So it's like this length right here. Because you can see the tangent line is a decent approximation for the function for values close to c. So I just moved a little bit to the right of c. I have this point on the tangent line. You can see that that little dy right here is not much different than the full delta y, which went from here to here. Now, as I let delta x go to 0, right, then that delta y is going to get closer and closer to dy, because these points will get closer to this point over here. It'll move down here closer to c. So the difference between the tangent line values and the curve values gets smaller and smaller, and the difference between my delta y and my dy get less and less, to the point where it's almost negligible. So I can use dy to approximate a change in y based on a very small change in x. But remember, it only works for changes in x that are really small. So we're going to be looking at really tiny decimal changes. So let's just take a look at this comparison one more time with like an actual example. So we're going to find the values of dy, the differential of y, and delta y, the actual difference between two y values. So I have this function here. This would be like my f of x. To find dy, I always start this way. I always start by just finding the derivative of y with respect to x. I just start by finding my f prime. So my derivative of y with respect to x, I'm just going to use the constant rule and the power rule, would be negative 4x. So then my differential of y is just that derivative times my differential of x, according to the differential formula. So if I want to calculate it for when x is negative 2 and for when my delta x, which is close to 0, so I'll use it as my dx, is 0.1. So I'm just going to plug in negative 2 for x and then 0.1 for dx. So I end up getting positive 8 times 0.1. Maybe I'll just write that real quick, which is 0.8. So this is telling me that when x changes from, so let's write it this way. So x is negative 2. X plus delta x would be negative 1.9. It moved 0.1 to the right on the number line. So they're very close together, okay? So what this is saying is that when x changes from negative 2 to negative 1.9, y will go up 0.8. It'll change from its original value to its new value by this much. So that's what this is saying. So now let's see how close it got. So let's find actual delta y. Actual delta y is when you take the y value at negative 1.9. So I'm going to evaluate f of negative 1.9 and then subtract the other y value. It's like a literal change between two y values. So I'm going to plug in negative 1.9 in my equation for x. I'm going to get a value for that, and then I'm going to subtract whatever I get when I plug in negative 2 for x. So when I plug in negative 1.9, I get negative 1.22. So that's the y value evaluated at negative 1.9. This would be like my f of x plus delta x, my new y value at my new x after I changed it a little bit. And then when I evaluate this function at negative 2, I get negative 2. This is my f of c, or my f of x. So subtracting them will help me find the change between y. So I basically get negative 1.22 plus 2, which is positive 0.78. So my y value actually went up 0.78. This is the actual change in y. This is my delta y between f of x plus delta x and f of x. But look how close my differential was able to get. It was only off by 0.02 or 2/100ths. So, and 0.1 is close to 0, but I can get even closer to 0 and get even closer approximations for delta y by using dy. How about you guys try one? Okay, so let's see how you did. So to find my differential for y, I have to take the derivative of y with respect to x. So here's my equation. I just basically used a power rule. And then I want to split the differentials up. So I multiply the dx to the other side. And then I can go ahead and plug in my value for x and for dx, which is my very, very small change in x, very close to 0. So when I plug those in, I see that my y value approximately will go down about negative 0.32 from its original value. So it's from when I go from f of 2 to f of 2.01, it'll go down about negative 0.32 is what this is approximating. So then if we find the actual delta y, we can see that that is very close. So when I actually plug, so first of all, I get 2.01 because I'm looking at my next x value, which has moved to the right 0.01 from 2. So it's 2 plus 0.01 or 2.01. So when I plug that into my function for x, I got, well, I didn't write down what I got, but when I take that number and subtract what you get when you plug in 2 for x, this is the difference between them. So that means this number was lower than this number. So that means the y value goes down. So x moved to the right 0.01 and y dropped this exact amount. But look how close. I mean, it was correct up to 2 decimal places, and it was only off by about 0.0024, by about that much, which is about 24 10,000ths or 2,000ths, which is not very much. It was a very close approximation of delta y, but also my delta x was closer to 0. Remember, the closer delta x gets to 0, the closer delta y will get to dy. And the better of an approximation dy will become for that related change in y. So remember, x made a certain change, and it had an effect on the y value. The y value also changed. And this dy helps us kind of see that affected change. So example 2 is more of an analytical question and just wanting to give you some practice with using this formula for finding the differential of y. So remember, the differential of y is the derivative of the function times the differential of x. So I like to begin by just finding dy dx, and then multiplying dx to the other side. So maybe first I'll think of y as a power function, right? X squared plus 1 to the power of 1/2. And I'll just use the chain rule and the power rule to evaluate that derivative. So the derivative of y with respect to x, which would be 1/2 times x squared plus 1 to the negative 1/2 power. So that was the power rule, and now I'll apply the chain rule, where you take the derivative of the inside part, which is 2x. And then I'll simplify a little bit. So I get dy dx is equal to, I can cancel out the 1/2 and the 2. This x can stay in the numerator, while this part that had a negative exponent will move to the denominator. And then maybe I'll write it in radical form from there. So 1/2 power is the square root. So that's the derivative of y with respect to x. This is nothing new from chapter 2. The only difference is when I'm thinking of it in the context of differentials, we like to separate the differential of y from the differential of x. So I would think of it this way. I would think of it as kind of multiplying the differential of x to both sides. And I would say, okay, dy is equal to this derivative times dx. I could even put dx in the numerator if I wanted to. Either way, you can either be off to the side like this or in the numerator. But that's pretty much it. So when you're finding a differential as an expression, you literally just find the derivative of the function and multiply it by dx. So why don't you guys try that down here? Okay, so in part A, I'm just taking the derivative of ln of 2x. So I begin by just finding that. And the derivative of ln of something is always 1 over that thing. But then I had to multiply by 2 because of the chain rule. And then those 2's canceled out. And so I just had the derivative of 1 over x. Or the derivative was equal to 1 over x. So then the differential for y is just that derivative times dx. Then in part B, I'm just taking the derivative of cosine of 3x. So I use the derivative formula for cosine and then the chain rule because of the 3x inside. So the derivative of cosine is negative sine with 3x inside, but then I have to multiply by 3 because of the chain rule. So then this is the derivative of y with respect to x. So then the differential of y is just that derivative times dx. Now in example 3, this is going to be more of an application of differentials where we are trying to approximate an unknown value of a function given a known value. So we're going to think of 3 as like my c, and then we'll think of 6 as my f of c, right? Because c is 3 and f of 3 is 6. So what we're trying to find is my f of c plus delta x. So we're going to try to find our delta x here. So delta x is the change between x values, which is negative 0.02. So my change is actually dropped. This x value is actually less than that x value. So c is 3, delta x is negative 0.02. So c plus delta x, that's my 2.98, right? Because that's 3 plus negative 0.02. So just trying to give some context to all these notations. So what I want to find, I want to find g of 2.98. Actually, maybe I should call these g instead of f, because we're referring to this function as g. So g of 2.98, I'm trying to find my g of c plus delta x. So if you remember the formula from above, I basically know that the change in y is when I take these two y values and subtract them. But that also means that if I add this y value to the change in y, right? The change in y plus my given y value will give me my new y value. Just add the change to y to the old y, it'll give me the new y. So this is one way that I could find g of 2.98. So I can think of this as the change in y plus g of 3 will give me g of 2.98. Well, I don't know what g of 2.98 is, so I'm not able to find delta y exactly. But remember, for delta x's that are close to 0, I can use dy to approximate delta y. Okay, so dy is equal to the derivative of g times dx. And if I want to find that when x is 3, then it would be the derivative at 3 times my change in x. So my change in x is negative 0.02, and my derivative at 3 is 3, because the point on the graph of the derivative was 3, 3. This means that g prime of 3 is 3. So this is 3 times negative 0.02. And then that is equal to negative 0.06. So this is saying that my y value is changing, is going down negative 0.06 from what it originally was. So I'm going to bring this over here. So I know that g of 3 is 6, and I know that if I add this change in y, I'm going to add this dy, that'd be 6 plus negative 0.06. My y value dropped by negative 0.06, or by 0.06. So my new y value would be 5.94. That would be approximately equal to my g of 2.98 if I use dy to approximate delta y. I just add that change in y to my old y to get my new y value. So we'll say g of 2.98 is approximately equal to 5.94. And that's one use of a differential. Now another very common or popular use of a differential is to measure something referred to as propagated error. And here's an example. So in example 4, it's saying, okay, the edge of a cube is measured as 20 centimeters. So this is the measurement using some kind of measurement tool to find the edge of a cube. But there's a possible error involved. It could be human error, it could be an error within the measurement tool itself. But there's a possible error of 0.05 centimeters when measuring the edge of the cube. So the question wants to now know, okay, well then what's the approximate propagated error for measuring the volume? So you might be wondering what propagated error is. Propagated error is when you initially have an error in measurement of one thing. So in this case, we measured the edge of the cube with a possible error. So you start with an initial measurement that could have some error to it. And then if you use that measure to compute another value, so like if we use this measurement of 20 centimeters to compute the volume, there will be some resulting error in that measurement as well, because you're starting with a measurement with some error and using it to compute another measurement. It's like a related error. This concept has a lot of parallels with related rates because we use differentials to talk about possible error. It's kind of like a change from the true value. And so when we used to do related rate problems, we would set up these equations and then we would take the derivatives with respect to time because we understood everything was changing with respect to time, and when one variable changed, it affected the other variable. It's the same idea here, except instead of thinking of these as changes in time, we're thinking of all these measurements as having a little bit of error. So there's a little bit of change between the measurement we got and the true value, and the change of one variable affects the change of another one, and we call that propagated error. The other thing this question is asking for is the percent error. So once you find your propagated error, you're basically just going to divide that by that measured value. So it's like how much out of the value was that error, and then multiply it by 100 because we're finding a percent. So it's basically just finding what percent of the value that error is, and then that's called percent error. So let's go ahead and try it with this example 4. So first of all, we recognize that this is a cube. So the volume would just be x cubed, assuming that we call the side length of the cube x, right? Because it's just, if you have a cube, and a cube is where all the dimensions are equal. So it's the base is x by x, and then the height is also another x. So when you do like length times width times height, it's x times x times x, which is x cubed. So like related rates, you have to start with a relationship between the two things, assuming there is no error, right? And then you use this differential formula. So don't forget, it's the derivative with respect to x times dx. And I always kind of start this way. You just take the derivative, which is equal to f prime, and then move the dx to the other side. Now in this case, I'm taking the derivative of volume with respect to x, right? dv over dx. And I just take the derivative of x cubed, 3x squared, and then I move the dx to the other side. So here I can easily see my differentials. Here's my differential for v. That's the propagated error in volume. And here's my differential for x. So this is my error in measurement of the side of the cube, because the side of the cube is x. That's the first thing we measured. And so there's the error in measurement of the side of the cube because it's dx. The dv would be the propagated error, the resulting or related error that would affect the volume. So I already know my value for x. It told me that it was measured to be 20 centimeters. So I know that x is 20. I was also told that my error in measurement is about 0.05 centimeters. So that's my dx, because that represents the error in measurement. And then I just plug those values in to find dv. But notice, I didn't plug them in until after I did my derivative. Very similar to when we did related rates. There's a lot of parallels here. So I plug 20 in for x, I plug 0.05 in for dx, and then I just simplify from there. So this will give me 1200 times 0.05, which will give me 60. So this is a propagated error in measuring volume, so that means it will be centimeters cubed since it's a dv. So if my side length measurement is off by 0.05 centimeters, my volume measurement, my related volume measurement, will be off by approximately 60 cubic centimeters. So you can see this little bit of error in measurement can relate in a significant amount of error in the related variable. And so we use these differentials to kind of approximate how much that error will be. Of course, the closer to 0 our dx is, the more accurate of a value this will be for delta y. Close enough that it can be used to understand that related error in y. So that answered part A of our question. Part B is wanting to know what the propagated error in surface area would be. So just like in related rates, we have to start by relating surface area to the side of the cube. So since the dimensions of a cube are all the same, it's basically composed of 6 squares. If I were to add up all 6 sides, they all have an area of x squared, and there's 6 of them. So the surface area of this cube is 6x squared. So I start first with the relationship between the edge of the cube and surface area. Then I continue by taking the derivative of the surface area with respect to x, use a power rule, so it's just 12x. And then I split up the differentials. So the differential in surface area, or the propagated error in surface area, will equal 12x times the measurement error in x. So again, the dx and the ds, these are our errors in measurement. So at this point, I can plug in my given values. I know that I measured the side of the cube to be 20 centimeters. I know that that can be off by about 0.05 centimeters. So I plug in those values to determine my propagated error in surface area, or to approximate my propagated error in surface area. So when I simplify that all out, this is all eventually equal to 12. Now, since this is referring to surface area, it's going to be centimeters squared, right? Because I was multiplying x times x. So it gives me centimeters squared. So that is the approximate change between the true surface area and the surface area we measure by using my measured value of 20 for the edge length. Now, lastly, in part C of this question, it wants us to find the percent error for the volume. So we're kind of going back to part A for this one. Part A, we found that the propagated error was 60. So what we want to do for percent error is use this formula here where you take that propagated error and just divide it by the measured value of volume. So I'm going to have to find what that would be if my side length is 20. So remember we said earlier that the volume is x by x by x, or x cubed. So if x is 20, then in this case that would be 20 cubed, or 8,000 centimeters cubed. So this is the measured volume using my measured value of 20, and I just want to determine what percent of 8,000 my 60 is. So I just divide the two. So my percent error in volume, according to this formula, would be 60 divided by 8,000, which will give me the decimal, and then I'll multiply that by 100 to get my percent. So I get 0.0075, which is equal to 0.75%. So the error is less than 1%. Not bad. So why don't you guys try this one here? It's looking at the measured radius and volume of a ball bearing, one of these little guys right in here. Use this formula here for the volume of a sphere, since these ball bearings are basically little spheres. And I want you to try to determine the propagated error in that volume and then the resulting percent error. Okay, so the two answers we get in this U-try are approximately 0.06158 inches cubed. Don't forget it's propagated error in volume, so our dimensions are cubed. That's our propagated error. That's our actual amount of inches that we're off. Then to find our percent error, we take that propagated error and divide it by what the volume would be if I used this 0.7 measurement for my radius. So when I divided those numbers, I got about 0.04286, which is approximately 4.3%. Now really quickly, the process I used is I started with the relationship between the volume of the ball bearing and its radius. Then after I established that, I took the derivative of the volume with respect to the radius, which is just using a power rule, 4 pi r squared. And then I multiplied the dr to the other side to get my differentials separated. That's when I took my measured value for the radius and plugged it in for r, and my measurement error, the amount that I was off from the true value, and plug that in for dr, because remember dr is referring to error in measurement. Multiply that out. So notice in one answer I left it in terms of pi, because when you divide by volume, the pi's cross out and there's less approximation and the answer is closer to exact. So that's why I did that. So here's the answer where I just multiplied 4 by 0.7 squared by 0.01 and got this. This is the value you'd get if you multiplied that by pi, just so you can kind of get an idea of how many cubic inches that is. Then for percent error, when I divided them, I left each value in terms of pi, so the pi would just nicely cancel out. And then I still had to approximate a little bit, but this is probably closer to accurate than it would be had I used the rounded value. Anyway, long story short, percent error is propagated error divided by measured value. Propagated error is just your differential for your y variable, which in this case was volume. So you just take your derivative, bring the independent variables differential to the other side, plug in values, and get your propagated error. Now our last example is perhaps the most challenging, and the way we're going to solve this is going to be probably a little bit of a stretch on your mind as to what's possible and what makes sense, which is exactly why I love it and exactly why I want to show it to you. Okay, so what we're going to do here is start with a given percent error. So basically this is saying that we have this right circular cylinder where height and radius are equal. You can kind of see they both have a value of 4. So the cylinder's volume is V equals pi h cubed, because normally it's pi r squared h, but if r and h are the same, it's kind of like just h cubed. So let's say the volume is to be calculated with a percent error of no more than 1%. So we want to make sure that our volume error is not that high, and we want to keep it under 1%. So we're going to kind of work our way backwards to figure out, okay, well then, how much error can be tolerated when we measure height, right? Because we know that if we have an error in measuring height, there will be a propagated or related error in volume. So we're saying we don't want that. We want that propagated error to be within 1%. So how much error can we tolerate with this measurement of h? Okay, and we're going to express it as a percentage. Okay, so what we're basically being given is the percent error of volume. So we're basically going in the reverse direction. Normally we start with the error measurement, we go to propagated error and then percent error. Here we're doing the exact reverse. We're starting with the percent error of volume. So percent error of volume has to be within 1%. So that's my dV over V. And it has to be no more than 1%. So we'll kind of think of that as less than or equal to 1%. Okay, and maybe it's probably better to think of that as a decimal, right, to help us when we're actually solving. So that's 0.01. So this is what we know, and what we eventually want to find, this is what we want eventually, is we want to know the percentage of error allowed in measuring height. Well, what would percent error of height be? It would be the error in measurement of height over the measured value of height. So we want the percent error in height. We want dH over h, which is going to be some decimal value, right? Okay, so how do I go from here to here? This is the cool part. Okay, so first of all, I'm going to do some side work over here. We take our volume, which is pi h cubed, and we start by just finding dV. Okay, so we'll say, well, dV, derivative of volume with respect to height, dV dH, is equal to 3 times pi times h squared. Then I'll take my differential of h and bring it to the other side, multiply it to the other side. So my differential of volume, my propagated error of volume, is 3 pi h squared times my measured error in height. Okay, so check this out. So now I'm going to plug 3 pi h squared up here in for dV and pi h cubed right here for v. So check this out. So I get 3 pi h squared dh divided by pi h cubed, and I know that that has to be less than or equal to, right, no more than 1% or 0.01. Okay, so the h's cancel out. These h's cancel with that, leaving me with 1 h in the denominator. My pi's cancel out, and I have 3 times dH over h. Okay, but remember how I was saying earlier, we want to end up with a dH over h fraction, which we almost have. We just have to multiply both sides by 1/3 or divide both sides by 3 so I can get rid of the 3 because I just want dH over h. Okay, so then I get dH over h is less than or equal to 0.01 divided by 3, which is 0.003 repeating, or 0.003333, etc. So what is that? That's my dH over h. That's my percent error in height. That means if I take this decimal and multiply it by 100, I know my percent error in height. So that would be about 0.3 repeating percent, or 1/3 of a percent, if I think of it as a fraction. Either way, 0.3 repeating percent or 1/3 of a percent. And that would be the allowed percent error in measuring the height. So that concludes our video notes. I can't wait to try these problems with you in class. I'll see you there.